Hello. I don't think anyone else has joined, so let's wait. Hi Sarang, hi Rohi. I hope you are able to. I hope you can see my screen as well. So, with that assumption, let's give it a start. So, what we are going to look into today is that, technically speaking, we have completed until this point in time the basics of statistics and probability, which we need to know. And now we will be looking into something which is known as inferential statistics. Now, before I go into inferential statistics, let me break this down basis my understanding or basis my thought process into certain parts. Okay. So I'll be breaking this down into three parts, and then let's see how we can take this forward. Yeah. So the first part that I would like to look into is otherwise known as hypothesis testing. Okay. We are going to look into things like central limit theorem. Then we are going to look into things like Z-score, etc. So there are certain tests that we're going to do. This is some kind of hypothesis, and we're also going to define what is a hypothesis and each and every terminology. So a few terminology will come. Then we have something which is known as more tests, as per me. Okay, so as per me, there are some more tests that we should always be aware of, which are like the variation tests, or otherwise known as, let's say, tests which are like ANOVA, the analysis of variance, right? So these are the kind of tests that are part of statistical tests. So I'll say more statistical test. And then there is a third kind of a category where I think there are certain things which fall into place, which is just things confused as machine learning problems. So I'll call them statistical modeling. Okay. So these are cases where there are certain aspects which may feel like a kind of a machine learning problem, but it is not a machine learning problem. It is actually a statistical problem. It is a statistical question. And whatever we do to answer those questions, whatever we do to approach the solution of those problems is entirely statistical. There is nothing to do absolutely with the machine learning. So, in a sense, as you can see, we're not jumping into machine learning right now. We have certain things also to cover. And I believe I can just quickly have a look into our curriculum. If I have that file open, let me see. If I have that file open, then maybe we can see what we are supposed to cover. So yes, so we are doing this. So we are already done with this, and we will be looking into this hypothesis testing and goodness of it. And then there are certain tools that we are going to look into. Excel and Anaconda, to some extent, we have already looked into, and we will be using these very precisely. We will have some brief idea about what is K9 and what is Weka, because there are industry use cases for these tools. So we will have a quick look into them. Then maybe we'll look into SQL quickly. Right. So after we have finished this statistical testing kind of thing and advanced statistics kind of things, we will not touch dimensional reduction techniques right now. Maybe we can do it at a later stage. Then we look into SQL, and then we can proceed with the rest of the mathematics and the rest of the predictive modeling areas which we have. Right. So keeping this in mind, let's start with the statistical inference part. Now, if I want to do statistical inference, I should be entirely aware of whatever distributions I have learned earlier and what their essence is, and taking that as a basis, and I'll simply assume that we know or we have understood what their bases are. Let's try to take an example. Okay, we'll take an example and then we are going to clarify a few things. So let's say I have, I don't know, I have, let's say, 1,000 students in my college. Okay, I want to know if I'm doing this, then why not write it here? Give me a moment. Yeah. So we will take an example. Let's say uh, I we have 1,000 students in our college. I would like to know if everyone has a bad opinion about the teaching skills of any teacher X. You may have already faced this when you are into college, because there is always a scenario where you'll come to know that there is at least one specific teacher whose teaching style is something nobody is able to digest. We don't know why. Maybe he's not doing it in a right way. Maybe he's doing it in a right way, but you're not able to digest it and so on. But there is always a problem with this specific teacher where we are not really happy with what he's teaching us. Okay, we are never happy with what he's teaching us. I just want to do kind of a survey, and I would like to do the survey in a different way, in a statistical way. I don't want to do it like any other survey where we are doing in our country, let's say the exit polls. So I don't want to do the survey basis or in the form of an exit poll. I want to do it in a different way. I want to do it in a more statistical, or let's say mathematical way. So is there any way I can do that? The answer is yes. Now, before I do that, what I would like to do is that I would like to understand, not 100. Okay, let's say 1,000 students in our college. We have a lot of batch, and considering all the years and all the batches, we have 1,000 students. So in this case, let's say I've taken a sample of I don't know, 30 students. So 30 students becomes my sample. Okay, and then I start taking a rating of that teacher which I have. So from each and every student, I ask for a rating for that teacher. I have a scale of 1 to 5. So 1, 2, 3, 4, 5. You choose any number. I randomly select 30 students, and you have to give me a rating which is somewhere in this range, 1 to 5. You cannot choose anything like not applicable or something. You have to be very specific which number you want to select. So out of a scale of 5, you need to select at least one number. And that number should be, as per you, the representation of how good or how bad the teacher is. Right? And then I'm going to take some kind of decision about the teacher. Maybe I am going to replace him with someone else. Maybe I'm going to ask him to improve, and so on. Now, what essentially I'm trying to explain over here is something like this. If I have taken 30 samples, then let's say uh, in experiment 1, or in trial 1, the 30 students that I've taken as a sample give set a rating 1. Then trial 2, I get a rating of I don't know, 1.4. I can get a rating in fractions as well, because I'm taking an average. Okay, so this value you see over here is an average. Okay, so if I do an average, how do? I take all the ratings of all the 30 students that I've selected in trial 1, and then I divide by the number of students, which is equal to 30. I may get an average value. And that average value is obviously, it can be a floating point number as well. It can be a decimal. So I take this kind of things, and I do at least, let's say, a trial up to, I don't know, 50. I at least do 50 trials. I do 50 trials and get some kind of, let's say, ratings. Okay. So this is exactly what I'm doing. And then I'm trying to plot the means or the averages that I've got in each and every of this experiment. What I get looks, let's say, something like this. Okay. It may not exactly look like a normal distribution, and that is exactly why I've deliberately tried to draw this diagram in a way that it doesn't look like a normal diagram, because I don't want it to look like a normal diagram. Okay, give me 1 minute. Okay. So now what we will be doing is What is the mean of this mean? The mean of this mean is going to be where I have the peak, right? So the average value of the mean is going to be over here, right? And there will be some kind of a standard deviation. There will be some kind of a variation, right? The data flow again is on this direction. So I'm assuming a cumulative kind of a direction in this graph. Although it resembles a normal graph, I can't really say whether it is a normal graph because I need to validate all the scenarios of a normal graph, right? I know there are at least 4 to 5 rules I have to validate, then only I can say whether it is a normal or a normally distribution or not. Now, what I can say by some means is that if I would have taken only the data and plotted the histogram of the values that I have received. So let's say I do a histogram of the ratings that I've got. So some people give this rating, some people give this rating, some people give this rating, then some people give this rating, and some people give this rating. So I have only 5 ratings in place, 1, 2, 3, 4, 5. So that's why I have 5 bars. If I join 1, 2, 3, 4, 5, then I get a normal kind of a distribution. If this is a PDF and I'm trying to test and figure out if this is a normal distribution, then the sampling distribution can also be assumed to be normal. This is the first thing, which is kind of a very upfront kind of an assumption. But this shape may not always look like a normal assumption. Also, this kind of a sampling distribution may not really be a statistically correct normal or standard normal distribution. This is something that we need to figure out. We need to figure out using the tests. Right? 1 minute. Okay. Now, this is the first assumption. Going by this assumption, what I am going to say is that I am going to find out if everyone likes the teacher or not. Now, this kind of a question is really very vague. Why is this very vague? Is because there is a question of liking. Okay. So any question that has to be answered in a statistical manner must be converted into a statistically relevant question. And one of the relevant questions is something which we saw in the last class as well. So the kind of 3 questions that we solved using that data of the breakfast cereal can be called as data-driven question. This is a very important concept. We'll face this problem a lot when you're actually working. So let's say I'm saying that if there is anything beyond this value, okay, then I'm going to say the teacher is going to be bad. So if I have any rating which is beyond this value, I've selected a random value. Okay, this value is, let's say, a random variable xi. Anything which is beyond the random variable xi, if it falls within this area under the curve, then I'm going to simply say the trainer is not good, and I'm going to take some kind of a call. Right now, this assumption that I already have, why am I looking specifically at this side? Maybe back of my mind, I already have this assumption that this teacher is not good. I have some kind of pre-assumption, preconception about this end user, right? Because basis that only I've selected this as a question, right? I would have also selected a question like something like this. Let's say this is xj, and I want to know if the teacher falls in this area, which means he is extremely good, extremely. See, this is where the teacher becomes an average teacher. This is where he becomes a worst, but this is where he becomes best. So maybe he is one of the best teachers in my college, right? Why not I select a defining kind of a criteria over here? Why did I select a question which is here, and why not here? Because there is something psychological happening over here. Psychologically, maybe I'm inclined towards the fact that I'm already under the assumption the teacher is bad. Okay, the teacher is not good, and then I'm simply doing this statistical experiment to see whether my understanding or my assumption is correct or not. And if I am correct in my understanding, then I'm going to take some kind of stunt decisions. This assumption that I have made is otherwise known as a hypothesis. Okay, and there are 2 kinds of hypotheses that can occur. A hypothesis, a first kind of hypothesis that can occur is known as the null hypothesis. What we mean by a null hypothesis is also known as a status quo. A status quo is something like you go to any random 5 students in that college of mine with 1000 students, and they tell you the teacher is not good, and you come to a definitive conclusion without looking into the feedback or review of any other teacher or other students that this teacher is not good. This is known as status quo. Okay, this is somewhat known as status quo. Maybe without even asking somebody, you only looked at that teacher and somehow you felt really bad about that teacher. His body language or kind of the vibe that you got from that person was not good. You didn't get a positive vibe, right? And then you decided, out of the blue, without any test, without any math, you came to this conclusion: no, this person is not good. And if this person is not good, how can he or she be a good teacher? How is that human being going to teach somebody well if the human being itself is not a good human being? So this is an assumption that you've done by yourself. This is known as a null hypothesis. The exact opposite of null hypothesis is the other kind of hypothesis, when it's known as alternative hypothesis. So alternate hypothesis is where I am trying to prove or disprove that this teacher is not good, which means if my null hypothesis is the teacher is bad, then my alternate hypothesis is the teacher is good or average. Right? Anything which is not falling in this area, anything which is not in this area, anything which is not in this area is where? In this side. So in this side, I have excellent, I have good, I have average, and I have bad, because this is extremely bad. So I can say that the leftover part is actually a combination of extremely good and overall good teachers. So I can say that the alternate hypothesis is the teacher is either very good or he's okay. So that becomes the alternative hypothesis. But please remember, the alternate hypothesis has to be an exact opposite of null hypothesis. Right? Example given in the last examples that we have taken, or the last questions that we have taken until the last class. We have seen there are cases is what is the probability of the size of that cereal box, or the content size of that cereal box, any random one, is going to be 0.260 kg. In case of a hypothesis testing kind of a scenario, when we are looking at some kind of null hypothesis, what we can say, one of the examples that I can take is that I am supremely confident that I pick any box from the lot in the supermarket and the size of that box is going to be less than 0.260 kg. That becomes my null hypothesis. Without any testing, I simply assumed it. I've simply assumed it based on maybe a one-time experience. Maybe I went to the supermarket and we already saw last day, right? Some thing like 27% of probability is there that the size of the box content will be less than 260 grams. So let's say I am that unlucky person. I went into a supermarket, I picked up something, and then I picked up this cereal box as well. And when I went home, it felt weird, so I tested it. I had a weighing machine. So when I looked into the content size, it came out to be less than 260. Right? So I'm that unfortunate person who got that less than 260 wala box. If that is the case, then I bluntly say that this company is not good, because all of its boxes are containing less than 260 grams in weight, although they claim to have 295 grams in weight. Okay, so that becomes my null hypothesis. What is the alternate hypothesis? The alternate hypothesis is the size or the content side in any randomly chosen breakfast cereal box of this company will be greater than or equal to 260 gram. Why greater than or equal to? Greater than, I understand. Equal to why? Because in my null hypothesis, I did not say that the weight of the content is less than or equal to 260 gram. I said it is less than 260 gram. Right? In the null hypothesis, I said it is less than 260 gram. That is why in the alternate hypothesis, it will be greater than and equal to. This should entirely be different from this or opposite from this. So that's why we have also included the equal to sign, because that absolute value of 260 gram was not covered over here, right? This is the concept behind hypothesis. So when we do a hypothesis testing, we will often end up creating graphs like these. And then we are going to apply a technique which is known as central limit theorem. Basis this technique called central limit theorem, there are a few assumptions which this technique imposes. And then there will be a few tests like Z-score test, there will be a t-test, there will be a p-test, and so on. So there will be a few statistical tables that we are going to refer to. I don't think we are going to have time today to complete CLT, and then if we have time, we may go on to Z-score. But I can assure you this Z-score will look familiar to you, not the T and the P tests. Why? Because this Z-score is simply an extension of that Z value, which we have already calculated until the last class, right? But to do all these things, we need to know what is hypothesis, which you have already understood. If you have any questions, please do let me know. And then we need to understand what all are the assumptions which we are going to take when we do the mathematics, right? So as you can understand, we are following a pattern everywhere, right? Pattern recognition is a very, very important use case in, let's say, data science as well. But when we are learning about all these things, we are also following a pattern. And the pattern that we are following is very as simple as everything we are trying to solve in a certain mathematical or statistical way. And for each and every solution, we have some set of assumptions. This is going to hold true for the entire life cycle of data science. You'll have a certain set of activities that you are going to do, okay, which is actually driven by some kind of math. You're going to apply some math and then try to code this up into Python or R in any language. And there will be some kind of background assumptions that you're going to follow. Now, not to misuse the term assumption, this is not a confounding variable. Okay, an assumption cannot be considered as a confounding or a confounding variable which is affecting your outcome. That is not the case. You're doing some kind of assumptions, and we will come to see what these assumptions are. Then we will get to know what the essence of the assumptions look like, right? So that's until this point in time. So my hypothesis in this case was null hypothesis, is otherwise known as status quo, or my blind belief, okay, without with sorry with or without any statistical value, okay. And then I have the ulta, which is known as the alternative hypothesis. This is exactly the opposite of null hypothesis, okay. Usually, just a friendly note, usually a stats person would like to disagree, or is a very important term, reject the null hypothesis. This is the aim. Either he or she is going to succeed or they are going to fail. Let's say in this example case, because I have selected that first xi kind of a range, right? So my null hypothesis is what? My status quo is the teacher is not good. Alternative hypothesis is the teacher is extremely good or he is okay, right? Most of the time, being a statistician, my idea or my ideology will be to try and prove the alternative hypothesis, but many times I'm going to fail. So I'll have to say that I accept the null hypothesis. So of this experiment or of this statistical test that I'm going to perform to validate the hypothesis is known as hypothesis testing. And the outcome of hypothesis testing can be either I reject the null hypothesis, or I don't say accept, I say not able to reject the null hypothesis. Okay. The reason why I say this is because so as to keep some scope for the next statistician to give it a try. If I say that I am accepting the null hypothesis, then it is kind of a pressure, or it is kind of an acceptance kind of a thing that I have done with the statement, which I don't want to do, because then there is no point of doing any statistical games, right? Now that we have defined statistical terms like hypothesis testing, let's look into CLT. But what this inferential statistics thing looks like, a quick definition is going to help now, is that this is the branch of stats where we infer values. We may not predict anything. Okay. I say I may also say infer values or results. Okay, this is a very, very important thing. Please remember this when you are doing any form of, let's say, data science. Okay, the definition of inferential statistics is simply a branch of stats where we are trying to infer some value or we are trying to infer some result. In my example, we are trying to infer some result. We are not going to give it a number to the teacher that this teacher is worst by this number or by this value. I'm simply saying that the teacher is bad. Okay, so I'm trying to infer a result, right? We are not predicting anything in this case. Majority, 99% of the cases in statistical inference, we do not predict anything because we cannot. We will come to know why we cannot. This is not because it is a probabilistic game or something like that. Okay, but the intention of doing inferential statistics is not to predict anything. That is the reason why hypothesis testing is used exclusively when it comes to inferential statistics. When we move over and go to our machine learning kind of things that we are going to do, we are not going to use hypothesis testing in that case, because our hypothesis in case of machine learning, where we are trying to predict something, becomes the assumption or the setup of the problem statement itself. This will sound confusing right now. When we do machine learning, you will come to know. Example given, there is a machine learning technique which is commonly referred to as a machine learning technique. It is not, by the way. It is a statistical modeling technique, otherwise known as linear regression. So regression analysis is where I try to find out if there is any regressing relationship between two continuous variables. When I try to do that, people often say I'm trying to predict house prices or I'm trying to predict a continuous value. You cannot predict a continuous value. If let's say you want to predict my salary, just a quick example, my salary is, I don't know, 15.1 lakh per annum. I can also represent this 15.1 lakh per annum as 15 lakh per annum, because that 0.1 with respect to 15 is very small. Also, I can represent that 15.1 as this. Also, I can represent it like this. Also, I can represent it like this, and so on. So as you can see, there are infinitesimal values or possible number of values in which I can represent a continuous variable, because it is continuous. We know by the definition of a continuous variable, it ranges from minus infinity to plus infinity. It can take any value, right? It can have any indefinite scale. One output is going to be of one scale, the other is going to be of some other scale. So that is the reason why inferential statistics or statistical modeling is where we do regression analysis. Regression analysis is not a machine learning thing, because if it is a machine learning, or when it is used for a machine learning, then when we predict something, we do not take anything which is known as hypothesis. We cannot have a status quo. We cannot have an assumption in that case, because the assumptions are then going to be set by the modeling technique that we use. Okay, don't get confused right now. When we look into machine learning, we'll come to know, but as of now, please be aware of this. Inferential statistics is a branch of stats where we simply infer. Let me write this into capital, where we simply infer values or results. We may not predict anything at all, because that is not the purpose of the game. Okay, that is not the intention for which I'm doing this test. Right now, let's move over to another, or a continuation, let's say, of the same problem. The problem which we have in hand, we have 1,000 students. I have some null hypothesis and there is some alternate hypothesis. Let's keep these aside and let's concentrate on the very basic thing that I need to do. The very basic thing is I want to do a statistical test. So for that, I need some data. Without data, how am I going to do any test? I have 1,000 students in my college. I would like to know if teacher X is good or bad. I take a random 30 students, do trial one. Then I put those 30 students back into population. I take another random of 30, random sample of 30, call that trial 2. I get the average. I do trial 3, trial 4 until trial 50, right? If I try to plot this graph as the distribution of the samples, it looks something like this. As I told you, this is known as the sampling distribution, okay, or the sampling chart. This sampling distribution has a sample mean, and that sample mean is here. It also has a standard deviation, which is sigma, right? Because it is obviously going to have a variance as well, right? Now, if this is the scenario which I am doing, okay, then A sampling distribution follows a normal distribution if and only if the parent PDF follows a normal distribution. So the data itself, as I showed you using those histograms and things, if that if that follows a normal distribution, then over a period of time you will come to know that this distribution also follows a normal distribution. But it is also going to depend on a factor which is known as the size of the sample. And that is where central limit theorem comes into picture. Okay, taking a sample distribution, a central limit theorem, okay, states first of all a property and then a characteristic. So let's look at the property first, then we are going to look at the characteristic. The property is the mean of this sampling distribution is given by mu. Okay, and the standard deviation, rather than representing it by sigma, now I'm going to introduce a new concept. This is known as sigma divided by root of n, and this is otherwise known as a standard error, because this is belonging to a standard distribution where n is the number of samples that are taken in each churn. In this case, my n is equal to 30, right? Is that in some cases, this is the sample size. Okay, this is the size of the sample. Oh, I'm sorry. This will not be 30, this will be 50. I've done 50 trials, right? I have actually done 50 trials, so that's why it will be 50. Okay. Because I am dividing the sigma or the standard deviation of the original data by root over n, I am trying to minimize the value of this standard deviation value sigma, right? So if this standard deviation value belongs to this, the original distribution's PDF, and I'm dividing that by root over n, even if I'm doing a root, this calculation is going to decrease the value of sigma, right? Because I'm trying to decrease the value of sigma, statisticians have named them a standard error and not standard deviation, because my intention, this is the property that governs central limit theorem. Intention is to minimize the standard error as much as possible. How can we minimize? Can I minimize the standard deviation? The answer is no, because that is not up to me. That is not even up to the sample that I have selected. That may be dependent on the sample that I've selected, I'm sorry. But it is impacted by the responses given by the students, that I will have some value of standard deviation. I cannot control the standard deviation sigma, but what I can control is the number of times I'm doing the trial. If I'm doing the trial for 50 times, 70 times, 100 times, then this value increases. The denominator is going to increase. As more as the denominator increase, the total value is going to decrease. I will be able to decrease the standard error. And in inferential statistics kind of a terminology, this is known as the accuracy of the inference that we have made. The less the standard error, more is the accuracy. Okay, so standard error is inversely proportional to the accuracy, or the accuracy is inversely proportional to the standard error. The accuracy here refers to the accuracy of the inference, because we are not predicting anything. Okay, don't worry, we will take some examples, maybe not today because we have only 7 minutes left, but when we take examples, we will come to know what is standard error and what is exactly meant by the accuracy. There is one more term which is used interchangeably with the accuracy of inferential statistics, which is known as a confidence interval. Right? So the basic backbone of CLT, or central limit theorem, is that my objective in my life, like the short notes we used to write in English class when we were children, my aim in life, if I'm asked to write a short note of that 5-mark kind of a question, my aim in life as a statistician when I'm doing inferential statistics, decrease the standard error as much as possible so that I can increase the accuracy of my inference. Keeping this in mind, let's take the definition of a central limit theorem. The central limit theorem, and now I'm going to do a new share because I have a diagram which can show this in a better way. I hope you can see it now. The central limit theorem says, as the sample size increases, let's say this is violet color, or sorry, this looks like a maroon color. This pink or a maroonish kind of a distribution is, let's say, my sample distribution, or my sampling distribution, which I've taken out of those 1000 students, right? Over a period of time, if I increase the number of trials and I increase the number of samples, then my distribution will come to a normality. Even if it is not a normal distribution at the start, I increase the number of samples, I increase the number of trials. Ultimately, the shape of the distribution is going to come similar, exactly similar to a normal distribution. This is a proven fact. You increase the number of sample, anything which was earlier, let's say, looking something like this or maybe this, is over a period of time, if you increase the number of sample, it is going to look like this. Ultimately, everything is going to converge like a normal distribution. But please note, this is not the normal distribution or the standard normal distribution or of the probability density function or the cumulative density function. This is the sampling distribution. There is a difference in the way in which I have collected the sampling distribution, right? So the sampling distribution is what we talk about when it comes to central limit theorem, and it converges or it gets converted, let's say, from this form to this form over a period of time. If let's say the sample size in this case was n1 and sample size in this case is n2, and n2 is very, 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 very high as compared to n1. So the more I increase the value of the sample and it gets closer to n2 as opposed to n1, the structure is going to be a normally distributed sampling distribution. Now, what is the problem? I mean, what is the actual requirement that I have over here? Why am I so interested to make everything in a normal shape like this? I don't understand. The reason why I'm doing this is because of this. This formula or this representation is otherwise known as the empirical rule. And I have already discussed this briefly with you, if you remember, when I took the distances. I told you if I have a normal distribution and if I draw a line on any point on the y-axis y1, and then I take distance on both the sides of the mean as d1 and d2, then the distance is always the same. And that is exactly what is happening over here. This is the mean. This is the mean of the sampling distribution. Okay, in the range of one standard distribution or one standard deviation, I'm sorry, minus sigma to plus sigma, this is one standard deviation. This is where I have 68% of all the data. Then I have the second layer, okay, which is 2 standard deviation. So minus 2 standard deviation to plus 2 standard deviation. This is where I have 95% of all the data. And last but not the least, I have plus minus 3 standard deviation, where I have approximately 99.7% of all the data. Right? So everything falls within that range. Everything is going to fall within that range. This is a cornerstone of central limit theorem. Saransh has raised a hand. Go ahead, Saransh. We have only 2 minutes. Maybe we can give a stop here.
Okay, so Bhomik, this will be standard normal distribution, right? Rather
Yes.
than simple normal distribution.
Yes.
Okay, so the central limit theorem, it says that as you increase the samples, it will tend towards standard normal distribution, or it will uh, tend towards a normal distribution.
Normal distribution.
Okay.
It will tend towards a normal distribution, but over a period of time, you will find that there is hardly any difference between a standard and a normal distribution.
Okay.
Because as you increase the size, it is all the same.
Okay, so even for a normal distribution, we can assume this 68%, 95%.
Yes. And it is not really an assumption. This is kind of, let's say, a hypothesis. You can say this is also a hypothesis. And this is where you have, let's say, the mathematical formulations of the percentage of data that falls into this kind of a category.
Okay, I got that point. I got it.
Okay. Now, before we close this, because we don't have time, let's take a very simple example and make it a stop. What if the mean rating of that teacher of mine is, let's say, I don't know, 3.2? Okay. And I have got a certain question that what is the probability of getting a rating which is only 0.7 or what is the probability of getting a rating which is 4.7? Let's say this is the negative side, right? So there will be 0.6. And what is the probability of getting 4.7? Using this rule, this set of rule, this is otherwise known as an empirical rule. Empirical rule can help me predict the probability without using any value, any score at all. I can clearly say it falls within this range.